Hi everyone, I'm Jiahua and I come from University of Padua.
And my name is Alejandro Dinkelberg from the University of Limerick. Welcome to our Sum of HPC program, Performance of Parallel Python Programs on ARCHER2. With the help of the EPCC, we use HP sister systems Osiris and ARCHER2 to investigate different performances of Python code. We mainly focus on ARCHER2, which is built on 128 AMD cores. Studies investigated performance improvements on Intel systems, but they're rare on AMD systems. We use Python because of its simplicity and its broad application, like in data science. Nevertheless, their readability and the dynamic typing slow down the performance and make Python unattractive for complex calculation with huge problem sizes. So we will deal with what are the best ways to speed up Python, how will the performance look like on the HPC system ARCHER2, and what does it teach us. We take an example from the computational fluid dynamics to evaluate the performance of our code. It computes the flow pattern of a fluid in a two-dimensional cavity with an in and outflow. We calculate each section by defining a grid, and for each grid point we compute the velocity of the fluid by averaging the value for its four nearest neighbors. This is given by the steam function psi. Additionally, the Reynolds number determines the viscosity of the fluid. We can only approximate the solution by solving the partial differential equation with the Jacobi algorithm. It calculates the psi for each grid point in an iterative process, meaning that the iteration will use a relatively high amount of computation time. The precision of the algorithm is determined by the scale factor, and our smallest problem size is 32 by 32 matrix. Here we focus on a scale factor of 256. In the end, after n iteration, the algorithm converges and provides us with the flow pattern. Scaling up the problem size will lead to a notably slow performance for our naive Python version, but there are ways to improve it. First, we can optimize our code and use packages made for numerical calculations. The well-known and widely used NumPy package, where we can accelerate our matrix calculations. Also, we could apply NumExpress or Numba. Second, thankfully, we can divide the problem and spread it over multiple nodes and processes. With the help of MPI4Pi, we have a message passing interface to communicate between processes. Third, parallelize your code not on CPU but on GPUs. By design, they are made for running hundreds of multiple device cores. For example, number encoder can help here. To parallelize Python code, we use a one-dimensional domain decomposition. We narrow down the problem into smaller ones by dividing it into slice subgrids. Like this, the calculations of each subgrid can be computed by one processor. We parallelize the code, but we have to enable the communication between the processors. Halos are boundary layers of each subgrid that are shared with another neighboring subgrid. If the halo of a subgrid is updated and it's informed by its neighboring subgrid, this subgrid updates and informs what was updated. In order to keep the halos up to date, a halo swap will be done. You've seen how to parallelize with Python. Now let's go to the architecture we use.
Our work is based on ARCHER2 and mainly use Cray compiler and Cray Python. We ran the Python programs and found that the NumPy version had better performance, and we analyzed the hotspot function was Jacobi stepwards. Then we optimized the programs from two ways. One was to optimize the NumPy arrays computation using NumExpert. In details, the original arrays computation is complete through double loops, so we called it naive Python, while the NumPy version allocates memory at first and updates the array internally, which greatly improves the efficiency. For NumExpert, we use the evaluate to accelerate NumPy arrays computation. The other was to use Numba to port naive Python program to single GPU, while comparing performance to the CPU. Now we can find that the performance of naive Python running on GPU is better than other programs on CPU. We can also find that the NumPy version optimized by NumExpert has stronger performance than the original one, even compared with C and Fortran programs. Next are the results of MPI optimization. In order to better evaluate the results, we mainly focus on CPU platform. Therefore, we decide to use NumPy version results as our baseline. In the single node but multi-process environment, the program's speed up increases with ranks. Before A ranks, the Python has no advantage over C and Fortran, but after 8 ranks, Python with NumExpert is close to C and Fortran. From the small figure, we can also see that the effect of NumExpert increases with ranks. However, if we continue to increase ranks, The advantage of non-expert will not exist, especially after 256 ranks. Combined with small figure, the scalability of Python NumPy MPI is very good, in fact slightly better than linear. The C and Fortran scalability is massively superlinear, presumably because of cache effect. As the local problem size gets smaller, it suddenly fits into cache and gets a huge performance jump. However, the Python programs do not get this benefit. Now Python can flexibly solve scientific problems. Use of NumPy and non-expert can accelerate Python programs, and an MPI4Py can help for good performance in a certain number of processes. C and Fortran still have advantages in large-scale computing, but we will continue to investigate the performance of Python in large-scale computing, including GPU platforms. So in the future, we can continue to investigate large problem size and more nodes on ARCHER2, and develop multi-GPU CFD Python program on the supercomputer Cyrus with GPU nodes. Finally, we would like to thank you for a fantastic visual summer of HPC. We have learned Python HPC skills, which will be of great help to our future. Thanks to our mentors Davey and Stephen, to the Summer of HPC organizers, and to friendly partners. That's all. Thank you for your watching and listening.